Chem 120. The semester may be winding down, but we're actually starting the most exciting, in my opinion, chapter of the semester. So chapter 8 is all about bonding, and it's our opportunity to start to develop an understanding of molecules as three-dimensional physical things, which is exactly what they are. Up until now, when we've been evaluating chemical reactions, a lot of our observations and our study has been limited to their physical properties. So a prime example there would be solubility rules from chapter 4. Now we're going to start looking at exactly why bonding occurs between two elements and be able to start drawing those bonds, which is awesome. Yeah, it is. Come on. There we go. Okay, so there's this key principle in science that I just want to write here in red so you never forget it, which is that form defines function. All right, you've seen me write this on the board a number of times, but I think that these carbon allotropes are really good examples of that. So both graphite and diamond are just carbon. Both of them are solely made up of carbon elements, but they have a different form, right? So here we have these hexagonal rings that form sheets, and those sheets have some attraction to each other, but not a lot. And that gives graphite a very important property, that it's slippery, and it's used as a lubricant for many different industrial purposes. Every key you've ever used is going to have that lock and key mechanism lubricated with graphite. Here we have a diamond. So again, these are just all carbon atoms, but these are in a very different structure than what we have over here. So here we have these nice thin sheets allowing for movement and flexibility. Here we have diamond, the hardest natural substance on Earth, and we have those carbons in tetrahedral arrangements to each other. So this is a word that you're going to learn in the second lecture of this chapter, but this structure right here would be tetrahedral. So that's having four atoms coming off of that central atom here. It's a really, really strong configuration. So both carbon, totally different physical properties. Why? Because the way that they are bonded to each other, their physical relationship to each other. Or you could think of that, more importantly, or better off, as their molecular geometry. Heck yeah. Which is basically this whole lecture. Spoiler alert. Okay, so why do bonds form anyway, right? We've been talking about them all semester, and so you should already have some idea why that happens. But the driving force for bonding to occur is that it's going to give the system lower potential energy. And actually probably it would be better to say that bonding, there's a D there, allows the system to achieve lower potential energy. And remember, lower potential energy equals more stable, right? There's less energy to hold. There's less energy overall in your system. Okay, so let's look at that from the perspective of the hydrogen atom. We have these two nice figures from your textbook. So here we have two hydrogen atoms that are far apart enough that they're not interacting. Here they start to come closer together. So this part here and this other figure would represent these two hydrogen atoms here. So the 0 line is essentially saying that there's no potential energy, right, relative between the two atoms. So here they start to come closer together. That would be these two hydrogens, right? So they're losing a little bit of that potential energy. But then we have the actual bonding of our hydrogen molecule. And notice that it's this distance between our hydrogens is such that it allows for the overall system of the energy to be the lowest, right? And so that point at which your two atoms that are forming a bond are at their optimum bond length is going to be that lowest point of potential energy, which is shown here as a negative 458 kilojoules per mole. Notice if you then took those hydrogens and tried to squeeze them together, you would have an increase in that potential energy, which is what this combination of hydrogen atoms is trying to demonstrate. So what's going on here? What's going on is that bond length is going to minimize repulsive forces while maximizing attractive forces. Right? Because you want to think about an atom as basically being a magnet. You have your positive core, you have your negatively charged electrons around it. You have two atoms close to each other. You're going to have those positive and negatively charged particles interacting with each other. This bond length for our hydrogen is consistent, right? So it's the bond length that we're always seeing for hydrogen. And that's because it is at that point that you have the most stable configuration. Most stable meaning the lowest potential energy. I like this figure here a lot because it is reminiscent, or it's trying to mimic those electron probability maps that we saw in chapter 7 when we talked about the shape of orbitals. So we know that each of these hydrogens would have just an s orbital, right? So let's just draw them like that, sure. But if you notice, the probability of finding an electron is much greater between those two nuclei than it is on the outside. And why is that? Well, because those electrons here are experiencing the pull of both of the nuclei, which means that they are more stable. They're going to be held more easily in place, right? Because everything in the universe is just ready to go flying off the rails. Yeah, it is. Okay, so we've already talked a lot about bonding in this class, and I've already introduced you to this concept of electronegativity and our periodic table. So we have electronegativity increasing as you go across a row, decreasing as you go down a column. I have liked to tell you guys that you can think of it as drawing a vector from francium to fluorine, where this would be your least electronegative, and this would be your most electronegative. Notice the noble gases are just not even here because they don't engage in bonding very readily. Okay, so we already knew this trend. Also, please take note that hydrogen is just like a floating orb, right? Hydrogen's interesting. It's in row 1 because it forms a positive 1 ion, but it's not a metal. So in this case, there's another instance of hydrogen being in kind of a weird place, which is that hydrogen and its electronegativity would actually be nestled between boron and carbon. So these values here are, there's a few different scales. This is the Pauli scale. I'm never going to ask you to know those values. What I will expect you to do is something that you've been demonstrating throughout this course already, which is understanding those differences in electronegativity. And now we're going to be able to apply those concepts in our bonding trends, right? Because now we have this additional tool of our electron configurations and orbital diagrams. Okay, so let's start talking about that. So we've explored ionic bonds and we have explored covalent bonds in this class. So just as a quick refresher, right? Because we have a final coming up and it's cumulative. Yeah, let's remember what ionic bonds are. That's going to happen between a metal and a non-metal. Right? There's a large difference in electronegativity. And there's this transfer of electrons. Okay, so you've known that since chapter 2. Awesome. So now let's look at an ionic bond. I'm like waiting for that to disappear, but I'm in a different program now. Yeah. So let's look at an ionic bond that can form between lithium and fluorine. So over here will be lithium. So make sure you have a periodic table near you, right? Because this chapter and chapter 9 are very heavy on the periodic table. So lithium's electron configuration would be 1s2, 2s1. So if this is our 1s, this is our 2s, this is 2p. That's going to look like my 1s shell is full, and now I have my 2s. Over here, for fluorine, I would have 1s2, 2s2, 2p5. And that's going to look like that. Okay, so these are our electron configurations. And let's remember a vocabulary word that we learned at the end of our last chapter, which is that this 2s and 2p orbital, oops, I forgot to label that one. Hold on, give me 1 second. These are our valence electrons, right? So those are the electrons that are in the outermost energy shell. So we can just think of that as the outermost in level. And those are the ones that are going to engage in bonding. Okay, so we're developing a model. We're developing a greater understanding of what we've got going on here. So let's just think about what we know about lithium and the kind of ion that it forms. I cannot. Weird. There we go. Okay. So we know that lithium forms a positive 1 ion and fluorine forms a negative 1 ion. And now we can start to appreciate exactly why when we look at our orbital diagram. So if lithium and fluorine are in the same environment, lithium can gain greater stability by losing this electron, donating it to fluorine, and fluorine also is going to gain greater stability. Greater stability, lower potential energy, right? You're also going to have that additional attraction of our positively charged lithium and our fluorine, creating that ionic bond. So it's energetically advantageous for this transfer to occur. So let's just kind of show that happening here. Crash landing. Okay, so after that transfer, I'm going to go ahead and get rid of this. What we'll see is that lithium's new electron configuration is just 1s, and fluorine's electron configuration, I'm just going to draw those valence electrons because those are the ones that we're interested in, right? Core electrons aren't going to be engaged in bonding. So in doing this transfer, lithium now has the exact same orbital diagram and electron configuration as helium. Fluorine has the exact same electron configuration as neon. So bonding, ooh, that's ugly, gives I just bought a better tablet and I can't wait for it to arrive. Let me erase that, sorry. So bonding gives noble gas electron configuration. Okay, so this was an example of ionic bonding achieving that. Now, let's do the same thing, but talk about it in the context of covalent bonds, right? So covalent bonds, ooh, it's a little fat. All right, so covalent bonds is going to be a nonmetal and a nonmetal. You have the sharing of electrons. And you have similar electronegativities. Okay, so key principles that you've known for a long time about covalent bonds. Now let's see it in the context of our electron configurations and orbital diagrams. All right, let's stick with fluorine because we've been talking about that for a little bit. Okay, so fluorine, we know it has our electron configurations. This is 1s, 2s, 2p. All right, and this one, we'll make that one red, sure. Okay, and now we're in a very different situation than what we had on our last arrangement. So over here, notice that if our goal is to get electron configuration that is identical to a noble gas, lithium had two possibilities of where it could go, right? So lithium's native electron configuration had just one electron here. So it either has the option, in order to achieve noble gas configuration, it can lose one electron, or it could have gained 1, 2, 3, 4, 5, 6, 7, which isn't going to happen because we know lithium is a metal. It has a lower electronegativity, right? And now we understand why it has a lower electronegativity. It doesn't want electrons. It wants to get rid of one because it would take a lot more effort to become the noble gas neon than it would take to lose one electron and become the noble gas helium. Same thing for our fluorine, right? Fluorine could gain one to become neon, or it would have to lose 7. That just doesn't even make sense. So of course that's not what happens. Okay. Sorry, there we go. Okay, so here's my fluorine. So we're drawing our very familiar homonuclear diatomic fluorine. Okay, so we have a different situation here because both of these want one electron, right? So we're not going to have a transfer, and in fact that makes sense. We know that F2 is going to be covalent. So instead what we have is this sharing of an electron, and what you can think of that as doing is essentially overlapping that last p orbital. A little more, of course it's a little more complicated than that, but in doing so, both of the fluorines, by sharing 2 electrons with each other, they both have noble gas configuration. So this fluorine in green would have the configuration of neon. You can think of this as being like a part-time donated electron. And over here, we have the same thing. So by sharing those electrons, they are able to achieve noble gas configuration. This looks like neon, this looks like neon. And the way that we represent this sharing of an electron is by drawing a single bond between them. This represents the sharing of two electrons, right? One of those electrons coming from one fluorine, the other electron coming from the other fluorine. Okay, so that's super cool, and we're excited. Now, let me get back over here. Yeah, magic, love it. We have thus far explored ionic and covalent bonding, but there's actually this intermediate as well, which is called a polar covalent bond. So before, let's go back over here, when we were looking at our fluorine, they're identical. They have the exact same electronegativity. So this would be a perfectly covalent bond. I need to change my nib. Okay, so perfectly covalent. Those electrons are shared completely evenly. So let's talk about what a polar covalent bond looks like. And let's use an example that we've used 1,000 times in this class. That would be our water molecule. And actually, I'm going to go ahead and go back over here. Okay, so our water molecule if you look at our electronegativity chart here, see oxygen has an electronegativity of 3.5, hydrogen has an electronegativity of 2.1. That's not insignificant. We also know that oxygen is a pretty big electron hog. It has a high drive to get electrons. We already know, because you've seen me draw it 1,000 times, that our hydrogens are slightly negative and our oxygens are slightly positive. Those are lone pairs. You're going to learn about those in our next lecture. But so this bond is not perfectly covalent. What that means is that the electrons are denser, right? There's more of them. Yeah, we can say denser. We talk about electron density. Around oxygen. So let's just say electron concentration. It's not the electrons themselves that suddenly became denser because they're around oxygen, but them relative to each other. Hopefully that makes sense. So basically, if you were to look at this, if you were to look at an electron probability map like we've seen before, you would have most of the electrons or greater electron density around our oxygen, and that is what is contributing to this slight negativity. Okay, so to quantify that difference, we have covalent as being perfectly covalent would be 0 in your electronegativity difference. Polar covalent is going to be between 0 and 2, and ionic is greater than 2. I don't expect you to have that memorized or to have these thresholds in place. It's also a little bit more rigid than I think we tend to use in chemistry. So I do expect you to know that ionic is your metal and your nonmetal. That's a large difference in electronegativity. Covalent, perfectly covalent, is going to be homonuclear. All right, so it's the same element bound to each other. So those carbon structures are homonuclear, right? Those carbon atoms have the exact same pole. They have the same electronegativity on the electrons engaged in bonding. Polar covalent is going to be, again, intermediate between those two. And so if you had like the nitrogen-oxygen bond, that's polar covalent. If you had chlorine and hydrogen, that's polar covalent. Generally, we don't consider the bond between carbon and hydrogen to be polar covalent, but it would not be incorrect to say that it is polar covalent. It's just in practice, there's really pretty equal sharing between the carbons and the hydrogens. But if you use this system, it would be polar covalent, and that would be perfectly fine. Again, it's a little bit more rigid than what we sometimes think of, although it's probably more correct. Whatever. Okay, so what does it mean to be polar covalent, and how does that kind of affect behavior? Well, you know, polar is coming from the fact that there are two poles. You can think of those two poles as being, again, like a magnet, right? You have your positive charge, or your positive side, and your negative side. So here we have hydrofluoric acid in a environment, and you can see all of the hydrogens are going to have this slightly positive charge. It's only drawn on one, but all of them have this relationship. And the fluorines, which are in green, are going to be slightly negative. Right, and right now they're just in an environment, and so they're just at totally random angles to each other, just floating about, having a good time. If you then were to apply an electric field to that environment, all of those molecules are going to line up such that their slightly positive pole is going to orient itself to the negative end, and the slightly negative will orient itself to the positive. So that's really significant, because this shows that depending on the environment, polarity is going to have a pretty big impact on behavior. And in fact, if you take organic chemistry, and you totally should, it completely changed my life. Thought I was going to be a doctor, took organic chemistry, and I was like, science. And it was the best decision I ever made. Okay, so it's very cool. So we need to be able to kind of make these assessments, and electronegativity is wildly important. So here's a nice kind of figure that's just showing you this spectrum, right? So this would be increasing in electronegativity. And you can see these differences in that polyscale are getting greater and greater. This is those differences there. So it's a continuum. Also notice this is 1.9, fluorine and hydrogen. It's a huge difference there. That's like almost ionic, which makes sense because we know that if this was in a polar environment, right, this is called hydrofluoric acid. You've seen me draw something like this before. What we're going to end up seeing is that dissociation of ions. Oops, and that was like an electron there. Kicking off a proton in solution, which makes sense because this is an acid. Very cool. Okay, so we have a way of showing that there's this polarity in a molecule, and we use dipole arrows. But before we get exactly to what those are, I want to start by just bringing your attention to these electron density maps. Electron density maps are really cool because they do a great job of showing that electrons really are like a cloud, right? So they are constantly in movement. We know that. They're waves and particles. Dual nature of our existence. But I like that this is like this egg-like shape, and it's showing that here we have greater electron density. We could also say that this area is electron rich. Over here, our fluorine in blue, or excuse me, our hydrogen in blue has less electron density. This would be electron poor, right? We've seen this throughout the semester. That's another way of designating that. So the way that we use dipole arrows is we always start with this like plus sign, and that's going to show that part of the atom, or excuse me, the molecule, that is slightly positive. Then you draw a line going through the nuclei to show the pull of the electrons towards that slightly negative sign. So to classify this molecule, we would say that this bond between hydrogen and fluorine, the bond is polar covalent. The molecule is polar. We could also say the molecule is dipolar, just meaning it has two poles. Or you could also say the molecule has a dipole moment. These are all equivalent statements. Chem 101 uses dipole moment. That just means that it's a polar molecule. Okay, well, it's not just as simple as evaluating the difference in electronegativity between two species, because we do have situations where, like we have down here, you have carbon being bound to oxygen on either side. So this is a symmetrical molecule. And so if you look at the electron density map here, and you imagine this molecule being put in that same electric field that we saw our hydrofluoric acid going into, this is just going to spin, right? Because we have two centers that are electron rich. So we don't have two obvious poles like here where we have our positive and our negative. If we were to draw our dipole arrows, we start with that positive, right? Carbon is less electronegative than oxygen. That dipole arrow goes through the nuclei, showing the pull of our electrons. Notice that they are equal and opposite, which means that they effectively like cancel each other. So there's a really important consideration here. Oh, I forgot that does that. Where here we have a polar covalent bond, but our molecule is not polar. Oop, I just put pop. Not polar, otherwise known as nonpolar. Okay, so nonpolar molecule, polar bond, right? Different considerations. In one, you're just looking at this bond between two species. When you're talking about a polar or a nonpolar molecule, you're looking at the entire molecule. There's a lot of really good practice in your recitation packet for this. Okay, so let's do just a couple more examples of drawing dipoles. I'm going to put the figures, the structures of the molecules on here. In the next lecture, you'll learn how to draw them yourself. So let's start with, this one's fun. So this would be CH2O. And if we were to, actually I'm going to use my other program. Oh, hey, we can leave that. We'll come back to it. All right, so we had CH2O. Again, you'll be able to draw that by the end of next lecture. Yeah. Okay, so this is our molecule, and the question is, do we have polar covalent bonds, and is the molecule itself polar? Okay, so our polar covalent bond would be right here. Right, there's going to be an unequal sharing of electrons between the carbon and the oxygen. Electron density is going to be greater around our oxygen. If we were to draw our dipole arrow, we start at that center of positivity going through the center of negativity to draw our dipole arrow. And then we would say that yes, this is a polar molecule. Right, here we have our water molecule. Right, hydrogen is less electronegative than oxygen. Those are polar covalent bonds. And so this is kind of a cool concept. If we were to add those two vectors, we would have a kind of aggregate dipole like so. So this is our center of positivity, negativity, polar molecule. Thank goodness, because water is so cool, and otherwise, who knows what kind of life we would have on this planet. If any, that would be sad. Okay, let's do one more example where we have that cancellation of our dipoles because they're equal and opposite. So let's do carbon tetrachloride. Right? Practice your naming because that is going to be on your final. Again, you're going to learn how to draw these. So right now you can just trust me, and then after you learn, you could come back and be like, did she do it right? Maybe I did, maybe I didn't. Maybe I was testing you all along. Okay, so here we have that tetrahedral configuration. Carbon is less electronegative than chlorine. So we can think about drawing all of those dipole arrows, such as, or like so. And so these are equal and opposite. So this is nonpolar. Right? We have polar covalent bonds, but the molecule is nonpolar. Okay, so this is just another illustration of the way that those can cancel each other out. So this was the carbon tetrachloride that I just drew. This is a nice ball and stick model. The lab is all about looking at these ball and stick models. If we were in person, you'd be able to actually manipulate them in space. If you take organic chemistry, which you totally should, you will buy one of these model kits. And then you will be as cool as me and have a protein on your desk just because you want to make sure anybody who comes over to your house knows the level of nerd that you are, right? It's perfect. Okay, so examples of molecular forms that can have this cancellation of polar bonds would be a linear molecule, right? Equal, opposite, non-polar. Right here, equal, opposite, right? 120-degree angles to each other, non-polar. And we just saw this one, equal, opposite. Totally messy, love it, non-polar. Yeah, and here's those electron density maps to kind of give you another view of that. Again, there's some nice practice in your recitation, and then I would encourage you in the recitation packet, once you get to just drawing Lewis structures, for each Lewis structure, it only takes a second to then make the evaluation of is this polar or non-polar. That becomes really important when you're talking about chemical reactions, right? Because we know that positively charged things and negatively charged things like to find each other, right? They're attracted to each other. If they interact, they're going to achieve a lower potential energy. That sounds a lot like a drive to bond. So if you had a molecule over here and a molecule over here, and they're moving around in random motions, like all things do, and they happen to bump into each other in that negative electron-rich area meets that electron-poor area, then you can have a chemical reaction take place. Okay. And that's it for this first lecture. So get some practice in and enjoy it. This is like the coolest. Totally goodbye.